So we have the kind of proposition here that X is a metric space, and if the UIs are subsets of X and they're all open, and there's a kind of unlimited number of them, you can have an infinite number of them, then the union of all of them is open. And for the second part, we have that if we have a finite collection of open sets, then the intersection of all of them is open. Note that here we can't have the intersection of an infinite number of sets being open, it's only a finite number of sets. So to prove this, well, first we'll prove the first statement. So as always, if we want to prove something is open, then we want to show that for any point in that set, we can take an open ball around that point, and that open ball will still be contained within the thing that we're trying to prove is open. So for the first one, we want to prove that the infinite union is, well, not necessarily infinite, but can be infinite union of open sets is open. So take X in, just take any point X in the union of open sets. Then X is in one of these open sets for some I in our set of indices I. But then since UI is open, but then since UI is open, there's an open ball inside contained in UI, which is also obviously open. So there exists, let's call the radius of the open ball epsilon, so there exists epsilon greater than 0 such that the open ball of radius epsilon around the point X is contained within UI. But then, well, we know UI is obviously in the infinite union, or just the union of UIs over all I in the set of indices I. But then the ball around X is clearly in, oh, that shouldn't be a U, that should be a union. And then the ball is clearly in the union. This holds for all X in the union. And yeah, so that means we've proved that the union is open. So the union is open. So for any point in the union, we can get an open ball around it, and that open ball will be in the union, thus the union is open. Now for the second part, well, what was the second part? It was if this finite collection of open sets, well, if we have a finite collection of open sets, then their intersection is open. So for this is slightly trickier than the first part. So take X in, what are we taking it in? We're taking it in the intersection. So take X in, let's just keep that up there while we write it. X in the intersection of all of these sets. This means then X is in then X is in each and every one of these sets. So X is in U1, X is in U2, and so on. X is in UR, so X is in all of this collection of open sets. Again, since all of these are open, we can get an open ball around X that's contained within each of these open sets respectively. So let me just write that down in words. Since the UI are all open, there exist and now all of these balls, they won't necessarily have the same radii, they'll have different radii. So there exist R1, these are just the radii of all of the balls, up to R. Well, yeah, so R is the radius of the rth ball, such that the ball around X is contained in the set UR. So it would probably have been better to choose the that to be N, but it still works. So there exist these radii. Since the UI are all open, there exist these radii. I'll put a comma there, such that so BR1 around X is contained in U1, BR2 around X is contained within U2, and so on. So BR around X is contained within UR. So now we pick epsilon to be the minimum of all of these radii. Minimum of R1 up to R, nicely named RR. So now if we take the ball of radius epsilon around X, then this ball, since the radius is smaller than all of these R's, is still going to be contained within each one of these open sets. It's just going to be smaller than all of these balls, but that's fine. So this ball is contained within all of these open sets. But then this is just another way of saying that this ball is contained within the infinite not infinite, just the intersection from I equals 1 to R of B. No, that's wrong. That should be the let me just undo this. It's not undoing, so I'll just write U I. So this new ball that we've made of radius epsilon is contained in the intersection of all of the UIs. That's just the same as saying that this set is open. So we found an open ball around the point X, such that it's contained for all X we could choose, such that it's contained within this set here. So i.e. I equals 1 to R, UI is open. And so that finishes the proof. We've proved both statements. So let's put an end of proof sign. Thanks for watching.